Now I want to talk about Lempel Ziv coding. This is the material covered in chapter 13 of Carver and Thomas. We note that construction of Huffman code requires prior knowledge, which is the distribution of source. We need to know px. But in order to figure out px, we need to spend a certain amount of computation. So Huffman code is good, but we need to know px. Huffman code does not make use of a correlation between the text time correlation structure that exists in English sentence, for example, is not utilized in Huffman code. So Huffman code does not make use of time correlation between characters or between words or between phrases. So if we had utilized these correlation structures, we could have saved certain description length. We can minimize the description length to the entropy rate or possible entropy. But that one was not utilized in Huffman code. So we could consider other type of encoding algorithm that does utilize this correlation structure. And one of the best ones that we had found is Lampersiv encoding algorithm. So Lempel Ziv Code figures out the correlation structure of the source in a sequence and compress further. So, and this Lempel Ziv code is a universal code, which does not require the construction of px. You don't have to find out px. And Lempel Ziv code, making use of the correlation structure, is dictionary based. So if there is a given text and we can have some vocabulary figured out used in this text, and then using the vocabulary rather than each single symbols or symbol frequencies, we can use the word frequencies and we can compress further. And also it is adaptive and very simple. So this very simple idea displayed by Lempel Ziv algorithm, we can compress the English text very well. So here is the operation. So operation is very simple. That the operation is simply described by this single sentence. Okay, so parse the data stream into segments that are the shortest subsequences not appeared previously. So this is very compact statement or operation statement. We can follow this statement, and that's the all that is required for Lempel Ziv coding. We can use example to entertain this operation. So here is the Lempel Ziv encoding, but once you are able to encode, you can do the decoding as well. So let's take a simple example for the illustration of the algorithm. Consider a data screen. In order to emphasize, in order to simplify the argument, in this data stream, I intentionally have only A's and B's. And then I have lots of repetitions of A's and B's so that we can have a correlation structure. And then utilizing the correlation structure, we can compress significantly. Okay, if A's and B's appear independently, right, then probably and equally likely, then we would not be able to compress much. So I want to use this very repetitive sequence of symbols as an example, so that I can show you that using the Lempel Ziv encoding algorithm, we can compress significantly. So the algorithm goes start from the left of the string. So we start right here, okay? Start right here. And as I move to the right, I parse the data stream into segments not appeared previously. So at the beginning, there is nothing in the memory, so we cannot find anything that has appeared already. So A is new item. So at the end of A, I parse it. So what I mean by parse is characterize this by comma, by placing a comma. So I separate this sequence with A. Okay, so that has never appeared previously. Now A has appeared. Then I read the next character, which is A, but A has appeared already. So I read one more character, and that becomes AA. AA together has never appeared before. So I parse it right there, okay? And I read, and what I read is B. B by itself has never appeared in the two items, in the two previous items. So I parse it. So B separately is a new word that I have encountered. And then I go on with the next, and then A, which has appeared in the first item. So I have to read one more character, and B, and A and B together has never appeared. So AB is a new dictionary word I have learned. This algorithm has learned. So AB, I parse it. And using the same procedure, B has appeared right here. So BB, I have to parse. A has appeared. AA has appeared. AAA, but has not appeared. So I have to parse it right here. B has appeared. BA has not appeared. So I parse it right there. And so on and so on. Down the line, I complete it. So once I have completed, I index it by the word that I have learned, or the word I have parsed, So first word, second word, third word, fourth word, fifth word, and so on, all the way up to 11th. And I do the encoding. So encoding goes this way. So A is new word, so A. I simply use this new word as that is the special case for the start. And since I have one word in the dictionary, now when I move to AA can be described by the word within the dictionary, which is A. So the first word and the new character, which is A. So what has appeared already in the dictionary can be represented by the index, which is 1, the first item, and the new item is A. And the third item, which is B, has never appeared, so I cannot find a word in the dictionary, so this is new. So it stays as it is. And then the fourth item, which is AB, A has appeared in the first word, and the B is new. So 1B. And the BB is, B is the third item, so third, and B is new item, which is B. So 3B, 2A, 3A, 6A, and so on and so on. And the convention is what has appeared, I have to use index. New character is just a new character. And in this particular example, I have accumulated 10 new words, 10 words in the dictionary that I have constructed. So in order to represent 10 items in the dictionary, I have to allocate 4 bits, right? So using 4 bits, I can represent these 10 items. So for the index, I allocate 4 bits. And then for new character, I use ASCII code. I use 7 bits. Okay. So using this encoding procedure, then I can represent this sequence using this encoding. Once I have done this encoding, I can do the decoding. So let's do the decoding. So decoding from encoded sequence is this, right? And then when I see the first item, I just decode it as A, right? And when I see the second item says first item and new character A. So first item is A and new character is A. Okay, that's the decoding of the second item. And the decoding of the third item is just B. So I have that. And then decoding of the third item and the fourth item is 1B. 1 is A and B is B. And 3B, the third item, is B, and B again, so it is B. Second item and B. Second item is AA and A, and so on and so on. As you can see, I can do the decoding, and then doing this decoding, I can reconstruct the original sequence back. All right, so that's the encoding and decoding. And once I have done this, let's figure out how much compression that I can achieve. So I have 11 segments per each segment, I have to allocate this many bits. So the total number of, so this is per segment. So total number of bits is 121 bits. And then if I haven't done any source coding, then I have a total of 24 characters. Each characters, I have to use ASCII code of 7 bits. So the total number of bits are 168. So this here is the compression ratio. So as you notice that if I have a more time correlation structure, and as I have longer sequence of characters, if I have a document with a large you know, amount of text, then I could have found more correlation structure. I could utilize words in the dictionary that has already appeared. So if I have more repetition, if I have a coherent English description of a certain event, for example, of you know, certain news item where you can have certain words repetitively appear in the text. In such a case, then you can compress a lot. And that compression algorithm can be easily described. I mean, easily obtained. Compression algorithm can be easily obtained by using this Lempel Ziv encoding. So Lempel Ziv encoding, without calculating the probability of occurrence of each word or each character, can efficiently compress a document where you have a lot of redundancies. We can entertain this example with these examples that I provide. This is Jordan's news article, but you can find any items in the internet. A news article or documents, and then you can compress with the Lempel Ziv coding. I have encoded this Lempel Ziv coding using MATLAB, and then you can do the exercise and see how much compression you can achieve by giving a news article as an input to the Lempel Ziv algorithm. So here is the Lempel Ziv algorithm. So here I use Jordan text, but you can use any text or document. So you read this document into the MATLAB environment, and then you can do Lempel Ziv encoding and see how much compression that you can do. All right. And for a homework, I have given you H1N1 virus sequence. Here is the sequence. So when you feed this into the MATLAB file that I have given you, you only need to feed in these parts. You just need to get rid of these numbers and feed them into, oops, oh, okay. Feed these sequence into the MATLAB file, then you will obtain the compression ratio. Okay, so there is an additional homework using this provided MATLAB file, and after you have obtained the experimental result, you can comment on your results by comparing it to the entropy of the source. And the homework set number 4 is due by 17-hour, October 23rd, basically this Friday, 5 p.m. You can upload it at the Kakao room. And Cover and Thomas, there are 9 questions. Okay, I think I am done with my lectures before the midterm. So that's it for today. And in the next video, we will talk about midterm problems.